All right, good morning. We're going to do chapter 5, section 5, which are called indefinite integrals. And the substitution method. Indefinite integrals are just that, is to have no bounds, no ends. So we have two types. Definite has an upper and lower bound.
I think it's frozen.
No. Yeah. The solution is finite. And then we have an indefinite, which does not have an upper or lower bound. Solution is infinite. I mean, it could be anything. And you always have a plus C at the end of it.
Is it possible to have a definite integral that has like infinite bounds?
No, then it would be bounded.
Okay.
Because when we have a definite integral, that means you have A and B are defined. They're actual values.
Okay.
You have basically what these represent are bounds on your graph.
Okay.
And that's the closed interval. Indefinite interval, they are from negative infinity to positive infinity themselves by definition, because it doesn't have an end. So what we're looking at here is this. The integral symbol, f of x dx. The integral of some function f of x. This is actually the derivative. What you're doing with integrals is you're seeing where did that come from? The original function. Since it's indefinite, you're always going to have a plus c because we don't know what the actual value is. If you have a definite integral, then what you're going to have is some value. These are going to be real numbers, and you'll have some number as an answer. So that's what we'll be looking at. So those are the differences. And after this, I'm leaving off some steps here. So from here, you would find the integral. And then we'd go here. So it's always the top upper bound minus the lower bound value. So this is what we're looking at. Because remember, what does the integral look for? Area under the curve. So from the curve to the x-axis. So what this finds is this tells us the area on this side for the upper bound minus, so this area minus this area leaves us what's between it. So that's what it's looking for. Let's see. I should get one of those. Yeah, so you have all this stuff written down here. So, basic functions integration. Let's look at that. The formula we're looking for is this. The integral of this is, since we're working backwards from the derivatives. Remember, in derivative, if this was a derivative, we put the n down and subtract one. But okay, let's look at that. So if we're looking at the derivative, it would be n x n minus 1. And that's what we end up with. So now integrals go backwards. In other words, we have to get rid of this one. And remember, this is 1 less than. So let's say this is 3. When we do integrals, we have to get rid of this 3. So we have to divide by 3. And where does this 3 come from? Add 1, 2 plus 1. And then where did this is the derivative, so it came from where? Plus 1. So the formula is, for the integrals, whatever you have, add 1 to the exponent and divide by that same plus some constant. Again, we have a constant because we don't have solid bounds. So this example here, x cubed, the integral of it would be what?
X to the 4th over 4.
Yeah,
Plus
so
c.
3 plus 1. Very good. So it's x to the 4th over 4 plus c. Now, again, why is it plus c? Because we don't know, it could be a 0, it could be a number. We don't know what it is because inside this function, we don't know what's in there. Now, what if the function itself was a complex function? We could define u as a function of x. So we can also take the integral of u to the power n du. And again, it's done the same way. U to the power n plus 1 over n plus 1 plus c. Here's the important thing. Before we go ahead and do that, we have to be in this form. In other words, whatever our function, because u is a function of, say it's x squared plus 1. So that's what u is, some power. We also have to have the derivative of this. So we also have to have du, which is 2x. So in order for us to take the integral of that one, we have to make sure we have, this is the u, the more complex is the u. And do we have du? Once you have u du, because then you can go ahead and put it in that form, which means we now have u to the 4th over 4 plus c, which is 2x plus 1 to the 4th divided by 4 plus some constant. So that's how we would use the substitution rule. You have to make sure you have u du. All right, let's look at example 1. Example 1. Find the indefinite integral of x squared plus x to the 5th 3x squared plus 1 dx. Yes. So we'll use substitution. Do we have a u and do we have a du?
Yes, x squared plus x is u, du is 2x. Correct.
So 2x plus 1. Well, that should be x cubed. It's x cubed, I'm sorry. X cubed plus x. Yeah, so it's 3x squared, right? So what we have here is we have u to the 5th du. Now, the question most asked, what happened to the dx? Because when we do the derivative of u, we're doing it with respect to x. So we have u to the 5th du over dx times dx. So these cancel. That's why we just have u to the 5th du. So our integral would be u to the 6 over 6 plus c, which would be x cubed plus x to the 6th divided by 6 plus c. Good. Right. Example 2 is another example where we may have to, if it's a constant that we're missing, we can include that in our substitution. Where's example 2? Example 2 is right here. Find this integral. So find the integral of square root 2x plus 1 dx. The first thing we're going to do is convert this to the form that we know. We have a power. So the u will be the interior part, 2x plus 1. The du will be 2. Notice we don't have a 2 anywhere there. So we have to put a 2. Since we put a 2 in there, we also have to get rid of it by putting a coefficient, because these two will cancel each other out. We're not changing it, we're just changing the way it looks. So what we have here is 1/2 integral of 2x plus 1 to the power 1/2 dx, which becomes 1/2 u to the power 1/2. This is du dx, actually.
Yeah, I was about to say that, like,
Yeah, it's just because du is automatically a function of x, so but it cancels with that. So we have add 1 to that. Add 1 to the bottom. Plus C. This bottom number, we flip it and multiply to the top. So we get 2/3 u to the power 3/2 plus c. The 2's cancel. So now we have u to the power 3/2 over 3 plus c. Put those back. We have 2x plus 1 and this can be simplified. Well, we could leave it like this, or we know we can simplify it like this. Which becomes
Is there another way to do it? Like any other answer that the computer would say?
I think it'll take this one.
Okay.
Because the reason being, because you're right, there are more than one way you could do this. You
Yeah.
could juxtapose those, but this is the simplified version. But I think it'll take this. If not that, then this is the one that takes.
Okay.
Are you saying that if we leave it as exponents, they're all three the same thing?
I mean, yeah, I was gonna say they're all the same.
The common convention of mathematics says since we started off with radicals, we have to end with radicals. That's what the rule of mathematics says. But because it takes more programming time and effort that people want to put into it, so they don't bust their butt for it. All right, so let's look at our theorem for the substitution rule. Theorem 6, the substitution rule. If u is a function of x is differentiable, what does differentiable imply? It's continuous, has all the points exist in the domain, whose range is an interval I, and f is a continuous function on I. Then the integral of f of g of x times g prime of x dx equals the integral of f of u. What does all that stuff mean?
It means the integral. Well, I mean, if you take the integral of a function, or f of g of x.
Well, if you take
Well, you're using u substitution right there, isn't it?
right, we're saying that u is the inside, but we also have to have the derivative u prime here. So we have u du. That's what it's saying. If you have that, then you take the integral, and then that's all you have. The substitution method to evaluate substitute, here's the steps for it. So let's look at this one. Example 3. So example 3. the integral of secant squared 5x plus 1, 5 dx. So the function f of x is secant squared x. We got to move. There. Thank you. And g of x is 5x plus 1, and g prime of x is 5. Remember, this is u, this is du, dx. Now, the reason we do that is we can rewrite this as secant squared u times du. It looks much easier that way. So the integral of secant squared is tangent u plus c. Now we have to put it back into terms that we know. Tangent of 5x plus 1 plus c. Example 4.
Oh, I was gonna ask, what happens to the 5 dx or the 5?
Actually, nothing happens to it. I'm glad you asked that, because we cannot use the substitution method unless we have f of g of x, g prime. In order, according to the theorem, we have to have this form before we go. So here's f, there's g prime.
Okay.
So because those fit, then we know that the integral is f of g, which is this. The question. The integral of cosine of 7 theta plus 3 d theta. Your question goes with this example. So what's missing?
We're missing a g prime.
A g prime, which is?
Fit inside of the function. Or
Yeah, so our f of x is cosine of x. G of x, which is the u, is 7x plus 3. Du is 7. So we're missing what?
we're missing the 7
So we put a 7 there,
and a 1/7.
107 out front. So we have 1/7 integral of f of u du. So the integral of cosine
Sine.
is sine u
Plus c.
plus c. So we have sine of 7 theta plus 3 over 7 plus c. All right, let's look at example 5. Example 5 now is a word problem. We have to determine what it's asking us to find. Sometimes we observe that a power of x appears in the integrand, that is one less than the power of x appearing in the argument of a function. We want to integrate. The observation immediately suggests we try a substitution for the higher power of x. For example, in the integral below, we see that x cubed appears as an exponent of one factor, and the factor is multiplied by x squared. Do I have that? Still have that. Oh, I'm missing it somewhere. So here's example 5. Is integral of x squared e to the x cubed dx. So do we have our f function
That would be x squared.
e to the x? Our g function is x cubed. Our g prime is 3x squared. So what are we missing?
So we have everything.
Nope. We have the e, check. The exponent of e is x cubed. The derivatives, we're missing a 3. So we got to put a 3 on, 1/3 out in front. So this may make it a little bit easier because we don't have a du. We have eu. We don't have a du. Because the g of x is u and the du is g prime of x. So that's where I have to put a 3 right there.
Would be the integral of EU is just EU, isn't it? Plus C.
No, the integral of eu is eu du. Well, it's going to be, yeah, but we can't do this because we have to have eu du before once we integrate it.
Okay.
Then we have a plus c. So this is the eu du. So it's going to be eu plus c. Yeah, we can't do that until we have a du inside the integral. So it's going to be e to the power x cubed divided by 3 plus c. Make sense?
Yeah.
I'm sorry. What's on my screen looks, that's why I was looking at the screen. I should have looked there. Example 6. Evaluate x radical 2x plus 1.
Is radical just an for
Square root.
square root?
Yeah, it's an nth root radical. That's what that is. Nth root radical. Right. So do we have all the pieces of the puzzle? Our u is going to be 2x plus 1. Du is 2.
We're missing a 2.
And then what about this x?
Not sure. From what I remember, they kind of just get rid of it, but I don't know how to get rid of it.
Okay, so we have our function is square root of g of x. or square root of u. U is that, du is 2. We need a 2. We have an x there. Let's see if we can do that. So this one's going to be x squared over 2 times 1/2 2x plus 1 to the 3/2 over 3/2. Okay, look, if u is 2x plus 1. Okay, let's figure out what is x. X is u minus 1 divided by 2. Okay, we can't. All right, yes, that's what we have to do. We have to figure out what this is with respect to u. So we have u minus 1 over 2. U to the power 1/2. Or d, which is going to be 2. We go further. We have u minus 1 and we multiply it by u to the power 1/2. U to 3/2 minus u half. Because since we have this just an outlier there, we have to get it in terms of u. So we have that now. We know that x is equal to, we know that x is equal to u plus 1 over 2. So we have U is equal to 2x minus 1. So it's u plus 1 divided by 2. So this becomes, okay, we're missing a du. So we have du is 2. So we need to put a 2 in there. X is equal to u plus 1 over 2. Du, that's du. So far, so good.
Mhm.
That means these cancel. No, they shouldn't cancel.
I don't know if this would help. I did this early on the computer.
No, that. That's cheating.
No, I did this earlier. Like I
Oh.
did, this is a question I think in the computer. And I got it right, but this is what I wrote down for it.
So at this stage here, we converted u to x. So what we have, okay, let's forget this one here. This is what we have right now. So if we put the 2, that's 1/4. U plus 1, u to the power 1/2 du. And that's what's going to happen from here is we have to distribute all this stuff out. Let's go with this. So integral of u to 3/2 du plus integral u to the 1/2 du. U to the 5/2 5/2 plus u to the 3/2 3/2 plus c. So then from there, we could distribute, which makes it u 5/2 over 10 plus u 3/2 over 6. And just put in that back in there. So we have 2x plus, or 2x minus 1 to the 5/2 over 10, 2x minus 1 to the 3/2 over 6 plus c. That's the answer. That's the answer I got. So yeah, what we have here is because we know how to do this one. It's this x right here. So when we convert this one, when we convert this part, we have u to the power 1/2. We just don't have this one. We have to take our function and make it into u, and that's what we did there. So it's going to be
Well, since
+1.
since the integral, or I mean, since the integral is, I don't know how to explain it, but if we're able to take the derivative of it, would it be able to go back to the original function
Of this one?
of the final answer?
Yeah, of this one? Yeah. It should be. Because once we take the derivative of it, let's do it. Let's try it. That's a good question. Check your answer. 2x minus 1 over 10 to the power 5 over 2 plus 2x minus 1 to 3/2 over 6 plus c. What is example 6 original equation?
The original equation, for example, 6 is the integral of x, radical 2x plus 1 dx.
So x, it's a u minus 1, not u plus 1. Because I was looking at my sheet, and it says 2x plus 1, so it means x has to be u minus 1 over 2. Okay, so it has to be minus. Okay, let's take the derivative of that. Take the derivative of this first one, we get 5/2 2x minus 1, subtract 1, we get 3/2 times derivative of the inside. That's the first one. Minus check out the 1/6. Now 3 over 2, 2x minus 1. Subtract 1 from that, you get 1/2 times derivative of the inside. Derivative constant disappears. So the 5 and the 10 cancel. The 2 and the 2 cancel. So we have 2x minus 1 to the 3/2. The 3 and the 6 cancel. The 2's cancel. So we have minus 1/2 2x minus 1 to the 1/2. And then this is 1/2 out here. There's 3/2 is 1/2 plus 1. We can factor out that. So we have 2x minus 1 minus 1. Something tells me that one of these guys should cancel out. Because if that's the case, then we have square root of 2x minus 1 times x minus 1. That 1 should disappear. Okay, where'd I go wrong? 10 goes out. 5 halves. It's 2 over 2 makes it 3 over 2. Six, so it's 3 over 2, 1 over 2. The 2's cancel. Okay, so the so it's 2's cancel, so it's 1/2, 2x 3 minus 1/2. We factor out the 1/2s. Take out the square root 2x minus 1. 2x minus 1 minus 1. Did it again. I did it again. The function I started off wrong. It's plus 1. So this one becomes minus. So the u is 2x plus 1. When I substitute it back, I got 2x plus 1. So it should be 2x plus 1 plus 1. And there it is. That's where they cancel. So I have square root of 2x plus 1 over 2 times 2x. The 2's cancel. So we have x square root of 2x plus 1. And that's what we start off with.
Okay.
My brain fart. I switched up the minuses and pluses, but it works. You want to see it?
No, I got it.
Okay, so let's look at example 7. Wow, that was a pretty big one. I'm glad you asked me to check it. Is because that's how you would check it. Yeah, it's we have to work ourselves backwards. Example 7. Sometimes we can use trigonometric identities to transform integrals. Integrals we do not know how to evaluate into ones we can evaluate using substitution rule. And that's where the cheat sheet comes in. So the first one is the integral of sine squared x dx. So we look at sine squared x is equal to what? We can say it's 1 minus cosine squared. And that's the same thing as saying 1 minus cosine 2x over 2. It's either a plus, it should be a minus since it's sine. Did you find that one?
I couldn't find it, but I think it's just because I can't see too.
Yeah, so this is what we look for. It may have sine squared u in there. So we rewrite this one as 1 minus cosine 2x over 2 dx, which take out the bottom 1/2, 1 minus cosine 2x dx. And we can do both these separately. The integral of 1 is x. The integral of cosine 2x. Look at you see if we're at the integral of cosine 2x.
Oh wait, that's 2x.
Big-
I thought it was a cosine square of x.
No, so that's I'm pretty sure it's 2x. I don't think it's because the whole problem is we can't integrate sine squared x. We couldn't do cosine squared x. So we're gonna change this one into 1 minus 2, the double line divided by 2.
Okay, what are we looking for?
The integral of sine squared x. And the integral of cosine 2x is sine 2x over 2 which becomes x over 2 minus sine 2x over 4 plus c.
Couldn't find out. No, this is the 2x part.
I don't know how to bring mine.
Found the half angle one, or at least how you converted it. Oh, can you go up a little bit?
So I'm doing this one. I take out the denominator, the 1/2 out in front. So I just have 1 minus cosine 2x. And I can take integral of both of these separately. The integral of 1 is x. The integral of cosine is sine. And then you have cosine u du. So we have to put a 2 in. So we divide it by 2. Because in order to do this one, we had to put a 2 there. And so we divide by 2. So now we have cosine u du, and that's our coefficient. And distribute to get rid of the parentheses. So x over 2, sine 2x over 4.
what I'm confused on is the
conversion.
The conversion of it. So
It's
it was 1 minus cosine squared x, and then you turned it into 1 minus cosine 2x over
right,
2.
right. Because I remember that for sine squared x, it's that. Cosine squared x, it's 1 plus cosine 2x over 2. That they're both similar like that. One's plus, one's minus.
And so we take the integral of 1 plus
Yeah,
cosine 2x.
so this is a
over 2.
constant we put out in front, and then we just take the integral of 1 plus 2 cosine 2x.
Okay.
Because that's cosine u, which is sine u du. We're missing the 2, so it's divided by 2.
Okay.
B, it says the integral, oh, perfect, cosine squared x. Because that one we can convert to 1 plus cosine 2x over 2.
So you bring out the 1/2.
Bring out the 1/2. Integral of 1 plus cosine 2x dx.
Then you use substitution.
Yeah, we're gonna integrate both of them. So we have 1/2 integral of 1 dx plus integral of cosine u, which is dx. So we have 1/2 integral of 1 is x. So this is cosine u. We need du, so we have to have a 2. And we put a 1/2 in front of it. This is cosine u. We need du, which is 2. So we put a 2 in front and divide it by 2. So we have integral of cosine is sine. Sine 2x divided by 2. Distribute. We have x over 2 plus sine 2x over 4. And C, get out. C is going to be the tangent. Integral of tangent x du. Okay. So tangent is made up of sine over cosine. That should be dx. And that's why I don't know why it's du. That should be dx. I should do that also. Okay, what do we notice about this?
The integral of a coefficient. Or not a coefficient, a quotient.
Well, is it whenever we have rationals, always see if we can have du over u. So if u is cosine, what's du? What's the derivative of cosine?
Negative sine of x.
So all we're missing is the negative. So we have the negative du over u, which means we have the integral of du over u is the ln, absolute value of u. So it's ln absolute value of cosine of x plus c. We're not done yet. We don't have a negative answer. In other words, you can simplify it even further. What do you do with coefficients? This is a negative one in front. That's the conversion rule. So if you have a coefficient in front, it becomes the exponent. Cosine x absolute value to the power -1, which makes it 1 over ln, or ln, 1 over absolute value of cosine x. What is 1 over cosine?
I'm still stuck on the exponent part.
In the coefficient?
Yeah, because I wasn't following up until there, or at least I got set behind.
You see where I got the negative though, right?
Yeah, I see where you got the negative from, and then you brought the exponent down, or you made the exponent positive by bringing the whole thing down and putting a one above it,
Yeah, I made that coefficient into an exponent.
and then one. Yeah,
And so now this part here goes on the bottom of the fraction. So if we had a to the power 2 times b to the power -3, it would be the same as a squared over b cubed.
okay, so 1 over cosine of x, or is it just 1 over cosine of x, or is it 1 over cosine of x, the absolute value of that?
It's the absolute value, because it's the absolute value that's raised to the power. And the reason for being because remember, you cannot have a negative.
No. What I'm asking is 1 over cosine of x equal to secant of x, or is it 1 over the absolute value of cosine of x?
1 over absolute value of cosine of x is equal to the absolute value of secant x.
Okay,
Because you cannot take you cannot take the ln of a negative number. So we have to make sure that this remains positive. And since the secant is a reciprocal function, it could be negative also.
okay, I see. But
Right.
that's just to make sure that the ln is not negative.
Yes.
Okay.
Yeah, in other words, if we had a function that was always positive, if we had cosine squared or secant squared, then we would need the absolute values because it would never be negative. Whenever you square a number, it becomes positive. All right, so let's look at example 8. Example 8. An integrand may require some algebraic manipulation before the substitution method can be applied. This example gives two integrals for which we simplify by multiplying the integrand by the algebraic form of equal to 1 before attempting the substitution. So what is it actually telling us? We're multiplying by 1. Does that sound familiar? You're according to what our sheet says, this example gives two integrals for which we simplify by multiplying the integrand, which is all this thing, by an algebraic form equal to 1. So we have to multiply by something here that's equal to 1 that will help us fix all this.
Well, so you're saying that we have to multiply it times something to make it equal to 1?
No, we're going to multiply by something that is equal to 1. That'll make this thing easier to work with. Because we can't integrate this one because we can't integrate this sum of difference on the bottom. If it was on top, we could split them up and take the integrals. But since it's one equation on the bottom, we can't do it. So we have to somehow fix it.
Can't you bring it up by making it a negative?
Not as plus or minus. If it was multiplied, yes, we just move both up, change the signs. But because it's a sum or difference, it's an equation, we can't just move it back up.
Do you multiply it to itself?
By itself, or what other form can we? Do you think we can multiply by?
Does it have to do with like natural log or something like that?
No. We do with ease. The first thing you always want to look at is the conjugate. Always multiply by the conjugate first to see if that works. What is a conjugate?
Yeah. Vocabulary is never my thing.
The conjugate of ax plus b is ax minus b. Example is x plus y, x minus y. If we multiply those together, what happens?
Would it just be, well, yeah,
Maybe that might help. So let's go ahead and try that. Let's try with the conjugate of this one.
okay. I think I remember this. We were doing something like this in Calc 2 and I completely was lost. I was like, okay. And I don't know. It's like when you see a step and you're like, okay, it goes from here to here, and that's all you need to know.
Yes.
It doesn't
Okay.
matter the vocabulary, you just need to know it does this to this.
That's true. And the vocabulary is the part that screws up more people than anything.
Yeah.
This,
Trying to explain the vocabulary is much harder than just seeing the process.
yeah, show me, exactly, just show me. And mathematics is a visual to me. It's always been visual.
Yeah.
Show me and I can do it. Great, we're getting close, but we only have one more example after this one.
You multiply times the conjugate. But do you just make, so you just make it you make it, I guess, minus and divide it by itself also, so it's equal to 1.
Oh, we're dealing with ease. Let's see what happens here. So on top, we'd have that. But see now, the problem we'd still have this on the bottom. See, our whole objective is we're having trouble with this equation because we have a sum on the bottom. Can we do anything? If we did this, let's see, if we did this, what will we have? We'd have the integral of ex minus e negative x e 2x minus e to the 0 plus e to the 0 minus e to the 2x. We can't do that because we just get the same thing on the bottom now. So instead of using this equation,
E to the X, E to the.
That's also equal to 1, because that way we're going to try to minimize our denominator. And what would that give us? E to the x dx, e to the 2x plus e to the 0 So what's that going to give us? So this gives us integral of e to the x dx, e2x plus 1. So if we say our u
What are you dealing at the bottom?
e2x plus 1, then du no, we can't do that because when we take a derivative of e to the 2x, we still have e to the 2x, so we can't do that. So what we can say is u is e to the x, and then we have e to the u squared, which is e to the 2x. So you follow that?
Yeah.
Because we couldn't do the 2 squared because that'll hurt. So we can't do that. We did that. We multiplied by e to the x. So now what we have is du u squared plus 1. That one, u squared, look for something that looks like this. Du u squared plus a squared on your cheat sheet. Or if you find u squared plus 1, great. But if not, then look for u squared plus a squared. On the integrals.
Yeah.
It's either going to be secant or tangent. No, tangent, secant will be.
Like the answer of it?
Yeah. Let me see.
Yeah, yes.
Okay, here was it. This is u squared, a squared. There it is. The integral of du a squared plus u squared. A squared plus u squared.
Oh, okay, I was looking for the second one.
And it's both. Well, it's not going to have a number because what it is, it's a function plus some number squared. And that's why they have, it's always going to be, if you notice, all of these are u's and a's, where a is a constant.
So let me get this straight. So we're doing the integral of e to the x dx over e to the 2x plus 1. and then that converts to the integral of du over these two.
Yeah, because we're saying that u is e to the x.
Mhm.
So what we have here is the integral of u squared plus 1, and that's the derivative. The derivative of u is eu, or ex. So we have ex dx. There's du. And that's u squared plus a squared. So it equals to tangent u squared plus 1 plus c. But yeah, that's what, when you look at those charts, that's what you have to look for. Now, look at the equation. Is it tangent u? Well, it's tangent u.
Which was it? It was du a squared plus u squared,
Mhm.
1 over a tan to the negative 1.
So it's 1 over a10. Oh, so it's 1 over a10.
Mhm.
A10 what?
To the negative 1. The tangents over, or to the power of negative 1. I don't know, it's weird.
Yeah, but this is saying, so it's saying that the integral of du u squared plus a squared is equal to 1 over a tangent u over a plus c. So what you have to do, this is the formula that's in there. What we have in ours, we have, so we have du is ex dx over e to x plus 1. And we said our u was e to the x. Our du is e to the x. And our a is 1 because it's u squared. On the bottom, we have integral of u squared plus a squared du.
Okay.
So we have to label our u is e to the x, our a is 1, because we now have to plug those inside this equation. So what that one looks like is 1 over a tangent u over a plus c. That's what negative means. It goes on the bottom. Or you can leave it as, so since a is 1, that doesn't go mean anything. We could leave it like this if you want. U is e to the x, a is 1. So our final answer is, yeah, so what we have to do is once we do our work, we know that this is our x, or our u, and this is our a. That's how those things work. All right, let's look at B. Let's look at secant. The integral of secant x dx. What's the integral of secant?
Integral of secant of x, or secant of u du is equal to linear, or the natural log of the absolute value of secant of x, tan of x, plus tan of x.
Plus c.
Usually what I do for these, or at least when they come up on the computer, I'll do the practice problem. And that's gonna become my formula to fix the next time I ever see the problem again. Because there's
And that's what you
times,
should do, yeah.
yeah, because trying to work it out is just like, okay, well, you're relying on a lot of like stuff that you may or may not know, or that you're getting out of like table.
Okay, yeah, so if you didn't have the table,
Mhm.
how would we go from here to here?
Well, you would find the trig identity for secant of x, right? Or like
Well, remember,
convert it, change it to something else.
it'd be 1 over cosine,
Mhm.
which would be cosine. Well, then we're back to the problem. It's cosine -1. So we don't have to do that with. So remember what is said earlier is multiply by 1. So what this one's saying, our 1 is secant x plus tangent x, secant x plus tangent x dx. This is our secant times 1. Now we go back and do all this stuff. So we have secant squared x plus secant x tangent x all over secant x plus tangent x.
And then secant x tangent x cancel out. So you're left with the integral of secant.
Well, no, all you're doing there is just canceling what you just put in there. No,
Oh, yeah, never mind.
you don't want to do that. Now, do we have a du here? Look at the bottom. If that's our u, secant x plus tangent x du, what's the derivative of secant?
Tangent square root of x.
Secant x tangent
Oh.
x, and the derivative of tangent is secant squared,
Okay.
and that's on the cheat sheet. So what we have here is du over u.
Okay, so the derivative of secant x is equal to secant plus tan of x, or times tan of x. And then
On
tan
the
of
top.
x,
Yeah, because you're distributing secant only to the top.
and then the derivative of tan of x is secant squared.
Right.
Okay.
So then in essence, we have du over u is the ln of u. So it's ln absolute value of secant x plus tangent x plus c.
Yeah, these are the only ones I would remember. Like, or at least try to remember, because I know they would be on this. Like, those
Well,
are the
see,
ones that they will always put.
and then we have here the integral of tangent is ln secant. So all these, and they're all absolute values because they can be negative.
Now, can I ask? It's a really subjective question, but where would this apply in the real world? Like, if you were doing
Anything that moves, you put it into terms of cosine and sine. Like, for example, if you have a trajectory of an object, any object, has a location, has an X and Y location. X deals with the cosine of that angle of trajectory times its initial velocity. And Y is the sine version of that. To your initial velocity times the angle of the trajectory.
So, okay, so I remember this. This is gonna go to physics most likely.
Exactly. Yeah. There you have real world. Anything that applies in physics applies in engineering.
Yeah.
Everything. There you have
Okay.
it.
No, yeah, because I mean, for me, I'm doing software engineering, but I'm trying to think of, am I gonna
Well,
use this
actually, yeah,
maybe about
because
making like diagrams or something like that?
yeah, or if you deal with anything that moves,
Yeah,
anything that moves, if you're designing programs for that, is you have to allocate for that
yeah.
aspect of it. All right, so let's look at example 9, trying different substitutions. The success of a substitution method depends on finding a substitution that changes an integral we cannot evaluate directly into one that we can. Finding the right substitution gets easier with practice and experience. If your first substitution fails, try another substitution, possibly coupled with other algebraic or trigonometric simplifications. There you have the clues. Finding the right substitution gets easier with practice. If your first fails, try another substitution, coupled with algebraic or trigonometric simplifications
So
to the
simplify
integrand.
it.
Do whatever you have to make it simple. That's what it's saying. Make it fit. Okay, so this one, example 9, is the integral of 2z dz cube root of z squared plus 1. I don't need the sheets anymore. No, we're done with the sheets. We're done.
Yeah, there's a next one.
All right, so where do we go? What do we do?
Uh, so you simplify the radical?
Well, let's see. The first one we're going to look at is, let's say u is z squared plus 1. So du would be 2z. Does that fit?
Uh,
So what we have here is du on top and u to the power 1/3 on the bottom. And that's the same thing as saying u to the power negative 1/3 du. And if we integrate it, we add 1 to the top, so it makes it 2/3, and 2/3 on the bottom, plus c. Which makes it 3 u 2/3 over 2 plus c. Three times z squared plus 1 to the 2/3 over 2 plus c. And that's our integral. All right, that works for me.